not. I may finish a little before the hour. We'll see how it goes. So I'm going to talk a little bit about my n-body code. This is the Galaxy code, which I have written and developed over a period of 40 years or so, and I have a nice manual to describe how it works, which you can see online. And this code is very efficient. It can run simulations of disk galaxies about 200 times faster than an average tree code, but it's not at all versatile. And that means that you cannot apply it to many problems that you might be wanting to solve in Galaxy Dynamics. It's good for disk galaxy simulations. That's my speciality. It will allow you to include moderately flattened pressure supported systems. You can allow for orbiting perturbers or embedded black holes or things like that, but it's not very good for handling mergers. If you want to have interactions between two galaxies, it's not really the best code to use. You'll have to use something less efficient. And so far, all of the components have to be collisionless, so it doesn't have any gas dynamical capability as yet, and I don't know whether it ever will. But I have, those are severe limitations, which means that you can only do a limited range of projects with this code. For example, it's good for testing the stability of an equilibrium model, as Mahmoud himself has already tried. And you can use the code to develop an understanding of bars and spirals, which is what I have done most of my life. You can follow disk halo interactions, which is the kind of thing that Victor did for his thesis. And you can compute the secular evolution of galaxies that are pretty well isolated. So the first thing that you should realize is that if you want to use this code, you have to choose a problem which that it can cope with. If you try to use this code for a problem that it cannot cope with, then you're going to be in trouble. So that was the first possible pitfall, is that you shouldn't be using this code unless you know that it's going to work for the problem you're interested in. Now, the reason that it's efficient is that it uses grid methods, which is very different from most people's methods of using n-body simulations. Most people use what are known as direct methods, either direct n-body or tree codes, which compute the forces between particles in a pairwise manner. But on the Galaxy code introduces a grid or raster of points, which could be either Cartesian, it could be cylindrical polar as illustrated in this figure, or it could be spherical. And any one of those three grids is allowed. The advantage of the grid method is that the field is calculated at the grid points very efficiently, and then the particles are accelerated as a result of the field. But the only masses that can contribute to the calculation are those that are within the grid. So if you have a lot of particles that have spilled outside the grid, then you're going to find that they're not going to contribute to the gravitational field, and the calculation will be compromised. So you want to be able to scale the model so that it fills as much of the grid as possible, leaving room for the evolution of the model to not spill too many particles, that really has to be less than a couple of percent. Should not leave the grid during the calculation. So that's a limitation. Now, in all n-body simulations of collisionless systems use some kind of softening of forces at short range. It's physically irrelevant in a collisionless system to try to compute the interaction between two particles that are very close by, because in a collisionless system, by definition, the forces that are important are those that arise from the distant matter, and the forces from nearby particles are irrelevant. That's true if you have enough particles. So it's and it's also numerically very inconvenient to have large, very strong forces at short range. So everybody, the right thing to do is to replace each particle by a mass cloud. So what you do is you soften the gravitational force, which means that each particle is smeared out into a density distribution which is centered on the particle, but has a core radius of a quantity called epsilon, which is the softening length. And of course, that immediately reduces the fluctuations in density on small scales, because they're all just eradicated by the smoothing. But then that, which is a real advantage, but it introduces a bias into the simulation, because you cannot resolve density structures on scales which are smaller than the softening length, and they're not well resolved until you get to several softening lengths away from the. So you're biasing your simulation against seeing anything which is going to result from high density, steep density gradient. And there's been a lot of papers written about what force laws should be employed in n-body simulations, and they're really the most important thing for everybody to realize is that it should be it doesn't matter. It should be a continuous function of the distance between two particles. That is important. It should be a smooth and continuous function. And when particles get close together, the separation is smaller than the softening length, then the forces should decrease smoothly to zero. And when separations are large, then they should quickly become the inverse square law forces that are familiar that are implied from Newtonian gravity. But how you asked him what functional form you choose that causes one behavior at short range and the other behavior at large range is not terribly important. And although there have been many papers written on that subject, in my view, if the outcome of the simulation depends at all on the choice of law between the two particles, then it's not collisionless, because the most important thing is the distant field has to be computed properly, and if it depends on how the near field is computed, then you're not really doing collisionless dynamics. And so if it matters, then you're still using not enough particles. Now, I mentioned that the Galaxy code uses grids. And it's important to understand how the forces between particles are computed using a grid. What you do is the mass of each particle, illustrated in the sketch here, is assigned to a few nearest neighbor grid points to the particle. Particle, of course, can be anywhere, and there's the raster of points which are regularly spaced. So it's in a grid cell somewhere, and you assign fractions of the mass of the particles to the corners of the grid nearest to where it is. And those are chosen to be close to biased by the weights of each particle. And the corner that gets the most mass is the closest corner, obviously. And then in order to conserve momentum, it's important that when you interpolate the forces, the accelerations acting on the particle from the grid, that you use exactly the same weighting scheme that you used to distribute the mass on the grid to start with. Otherwise, you will end up with particles which are able to accelerate themselves, which is not a good idea. So you need to have you do that, and you end up with accelerations between a pair of particles which will always equal an opposite, but not necessarily perfectly collinear, and that is something which results in some mild torque between any two pairs of particles, which you want to minimize if you possibly can. So the figure that I'm showing here illustrates in 2 dimensions. If you have a softening length which is as large as 2 grid cells, then and you use a Plummer softening law, then you find that the acceleration, this is distance squared times acceleration, so it should asymptote to 1 at large distances and go to 0 at small distances, as it does. And along this curve here, which I'm moving, where I'm moving my cursor, there are error bars there, but you can't see them because they're too small to see. And there are slight, this horizontal line here shows you the magnitude of the forces in the direction perpendicular to the line of sensors, which should be small and is, but as you can see, there's the small residual forces which appear at a distance of 2 or 3 mesh spaces. Now, when you go to 3 dimensions, you don't really want to use the Plummer softening law, this is an ideal softening law for 2-dimensional simulations. But when you go to 3-dimensional simulations, you really want the softening law to asymptote quickly to inverse square law. And so this is what happens in 3 dimensions. You use a different softening law. But then, as you can see, this is using the Cartesian grid. You get a little bit more worse force quality at short range. Now, you can improve the quality of the forces in these figures if you want by using, first of all, you could use a finer grid, which will mean that the errors will be confined to a smaller part of the total amount of the simulation, or you can play around with instead of using linear interpolation, as I've indicated in this figure, you can try using quadratic or even higher order interpolation schemes, which spread the particle masses over more points and interpolate over weighted sum over more points. There's 2 reasons why that's a bad idea. First of all, it degrades your spatial resolutions further because the masses are spread over bigger distances, and secondly, it takes an awful lot more computer time, and you're much better off using your computing resources to improve the number of particles rather than to improve the quality of the forces. And I'll come to explain why that is true in a minute. Now, when you want to use a polar grid, you have to be aware that as illustrated in the figure here, that the sizes of the grid cells get larger as you go out in radius. You have a very good spatial resolution right in the center of the polar grid, perfectly, really high spatial resolution where the forces are very well resolved. But as you get towards the edge of the polar grid, the forces between particles can become very strongly dependent on the grid in the outer parts. And if you've got a lot of mass in the outer parts, and the evolution of that, the particles in the outer parts become important for the physics that you're trying to solve, then you really need to worry about the fact that the grid is getting coarser towards the edge, and you must probably have to use a finer grid. So you should refine the grid until in the region where you're interested, the forces are adequately resolved. With strongly grid-dependent forces, you're asking for numerical trouble. A nice thing about polar grids is that you have this azimuthal periodicity, which means that you can apply a filter to the gravitational field, which removes the high azimuthal or sectoral harmonics, so that you're dealing with the low order mass distribution where spirals and bars have some significance, and the density variations in azimuth are important. But when you get to density variations in azimuth of 10 or 12 for the m equals 10 or 12, then you're really not interested any longer in those real density variations. Those can reflect nothing but the shot noise in the particle distribution, and it's beneficial to filter away all the gravitational forces that arise from high order sectoral harmonics. And so that really helps. It's equivalent to another method of smoothing, in addition to using the softening, which reduces the influence of noise on your system, which is important. Another thing that you need to worry about, and the Galaxy code will not allow you to do this, is you have to have the grid vertical spacing less than, or at least no larger than, the softening length. If that's not true, then the grid-dependent forces in the vertical direction are also going to be compromised. The third kind of grid that you could use is a spherical grid, which is kind of a funny thing. It's really just a set of shells in one dimension, and on each shell the code performs a surface harmonic expansion in the familiar YLMs from quantum mechanics and all mathematical physics. You expand the mass distribution on each shell in these components, and the more L's and M's that you include in your simulation, the more faithfully your code will, the calculation will try to mimic the effects of point mass forces between two particles. But and you can expand up to any order that you like. The code will not stop you from expanding up to 100 if you wanted to, in any order up to L of 100. But that's not at all desirable, because really what you're trying to do with these grids is represent a smooth mass distribution, and so you want to use the low order expansion on each one of these shells to filter away the effects of the individual particles and create a much smoother mass distribution. And so if you ask yourselves, what are the forces between two particles if I limit the expansion to L of 4, you find that the forces vary a lot depending on the relative positions of two particles. But you shouldn't worry about that. I mean, this diagram shows you how, to the extent to which they vary, and the black part shows you the forces between the two centers of the particles, and the red part shows you the forces perpendicular to the line of centers between two particles, and they're large, as you can see, relative to the expected value, which is at 1. But that's not a source of concern, because you've got millions of or hundreds of thousands of particles, and you're trying to represent just a smooth density distribution. And so the smooth density distribution is adequately represented by a small number of components. So if you think you need to use a lot, then you're using the wrong code. It's not the right kind of code to use. You just want to have a relatively smooth mass distribution, so you need an expansion to low order. If you try to expand up to, say, 32 in this diagram below, you can see the range over which the forces are wrong is significantly narrower than if you expand to L of 4, but the errors that you get are very much larger, even at short range, than they were in this diagram here, and so you end up getting strong and incorrect forces when particles are nearby, and that's the problem of shell crossings that people talk about in simulations that use this kind of method. And it means that if you have a mass distribution that is not a smooth, sort of mildly distorted spherical distribution, but you have something like a tidal tail or a thin disk or something like that, and this code really isn't very good for working with those kinds of, because the forces are wrong no matter how many L's you take. and you shouldn't be trying to crank up the number of terms in this expansion just to get forces right, because they'll still be wrong at short range, and they get worse. Now, one of the great strengths of the Galaxy code is that you could use multiple grids, and I do this all the time. I make extensive use of this hybrid idea, that you simulate a galaxy, in a disk galaxy on a polar grid near the center, which is absolutely ideal for representing the evolution of a spiral disk, which might want to form a bar or something like that. But that all is computed with very great fidelity on a 3D polar grid. But these you embed that galaxy in a halo, and the halo is going to extend well outside the visible disk part of where the particles are doing the interesting things, and you want to have be able to capture the gravitational forces from that, and so you want a large spherical grid, and you can have and you can assign the bulge, if there's a bulge in the disk, to the spherical grid as well, which is ideal for representing nearly spherical mass distributions. But it's important, and the code will achieve that, to compute the attraction between the halo particles and the disk particles at every step. They're always, all the forces are computed in a way that interpolated and taken into account between every pair of particles at every step. So that's all arranged for you. You don't have to do anything about that. The code will do that. You can also make the two centers of the two grids, if you want to, non-concentric. So you can use the code to compute evolution of interacting galaxies if you want to. I have and have the two grids orbit around each other. I have tried this a few times, and I have never been completely convinced that that the code is working, is doing the dynamics properly. At least as the two galaxies begin to merge, then all sorts of strange forces can arise, and so I wouldn't recommend. I have never published anything that uses the code in that way, and it's a capability which I think you need to be careful of if you want to use it. Okay, so I mentioned earlier that it's important to use a large number of particles in the simulation, and this is because the system, you want to. You're better off using your computing resources to increase the number of particles rather than to do to improve the interpolation scheme in particular. But if you once you've got adequate resolution in your grid, it doesn't help to increase that very much. You want to use your computer resources to increase the number of particles. And let me explain why. This is a study I made a few years back now, in 2015, of stable equilibrium models. There were three models that I used. There's a Hernquist model, which has a cuspy core, a cuspy center, a Plummer model, which has a uniform core center. And these are, the distribution functions are known and they're stable. You can set up simulations containing some numbers of particles that represent these two models, and evolve them using the spherical or different methods of the n-body code. And what these figures are plotting is the value of the virial ratio, the T over W, for those models measured from the particles. And you can see when the number of particles is only 1,000, which is a very small number, of course, admittedly, this virial ratio fluctuates a lot, and it fluctuates without decay. It goes up and down. There's no rising or decreasing trend across this. It's just a constant source of fluctuation in the virial ratio, and that's caused by shot noise as the particles are moving around. And what you should think about is dividing your model that you might have with a certain number of particles into subvolumes. And each subvolume contains a smaller number than the total number of particles. You can make those subvolumes very small or as large as you want. You just think about them as in this thought experiment. And because there are n particles in each subvolume, the forces that you get from the particles in that subvolume are incorrect at the level of n to the minus a half. That's just shock noise that's causing that. And effectively what you're doing is you're seeding your initial equilibrium model with a spectrum of density fluctuations, the perturbing forces right from the start, which come from the distribution of the finite number of particles. And what's happening in these simulations that I'm illustrating here is that the system is responding to the forces that come from these density fluctuations and causing it to oscillate in this way, in a non-periodic way, and that will be driving the evolution of your system that you thought you had set up as in equilibrium. And the only way to get rid of that is to increase the number of particles. So as I increase the number of particles by a factor of 10 and then a factor of 100, you can see the variation in the virial ratio dies down, but it's still fluctuating. And it's a very slow convergence because 1 over the square root of n is not a very rapid function. So you want to invest all your computing resources as much as you can in increasing the number of particles in your simulation to beat down this noise. So relaxation in an n-body system, which should be negligible if it's collisionless, is caused by the cumulative effect of distant encounters, and that in the case of these n-body simulations, you can see from what I just described that the perturbations come from the spectrum of noise in the system. And the standard relaxation formulae that you read in Binney and Tremaine and other places ignore the effect of these collective oscillations, and you want to try and see if you can measure the rate at which the system is relaxing, and that's what I did in this paper. And what's happening here is that sorry, I was trying to go to the next page. Happening here is that I'm trying to measure the rate at which the system is relaxing, which means that the energies of individual particles, which should be a conserved quantity, are changing. And so I can measure the diffusion rate of the energy of each particle in the simulations. And then if I take the Plummer model and I increase the number of particles across the from 1,000 to 100,000, then you see that the relaxation rate, the energy diffusion rate, roughly decreases as n to the minus 1, which is the dashed slope here. So that's pretty much what you'd expect. There is no Coulomb logarithm term because the resolution in these grids is fixed at that particular. So you get the n to the minus 1 dependence pretty much as you expected. And as a wrinkle on this study, I computed the forces between particles, first of all using my spherical grid, then using a tree code, and then using a basis function expansion, and I calculated the diffusion rate using the 3 different methods of calculating the gravitational field, and you can see they're in pretty good agreement with each other. There's a slight improvement in the field method, which I wasn't able to understand. But that is all 3 of them are following the same dependence, and there's a very small difference, about a factor of 3 between these methods in their ability to suppress relaxation. I'm using on the right-hand panel. I'm using, as I did before, particles of different masses. So if you've got heavy and light particles and the system is relaxing, you should find that the energy is being transferred from the light particles from the heavy particles to the light particles, and so the relaxation rate should differ. This is an attempt to show what the heavy and light particles are doing. The light particles are relaxing a little bit more rapidly, but in order to see any difference at all here, I had to scale the values by n, so that this is suppressing the real variation, which of course shows that the things are relaxation rates getting smaller. I just wanted to include the plot which I made from a uniform sphere, which is a pretty unrealistic mass distribution for a galaxy. But a uniform sphere has a harmonic gravitational potential, and that means that the spectrum of oscillations of density fluctuations that you excite can oscillate at a constant frequency forever because of the potential is harmonic, and so you get a very much different and much slower rate of improvement in relaxation. It goes as n to the minus a half if you have a uniform sphere. This is a curiosity and not really of any physical relevance to galaxies, but I included that. So the conclusion from this study was that relaxation can be controlled by increasing the number of particles, and mass segregation is not too bad in spherical systems. Now, another very important way of doing good quality work with n-body simulations is if you want to start from an equilibrium model, is to select particles in a careful manner. If you want to start from an equilibrium system, you really should, if you possibly can, find a distribution function that's appropriate for that spherical or that system, whether it's a disk or a sphere or whatever else it is. If you can find a distribution function which is an analytic solution of the for the evolution of the equilibrium model in a given potential, then that you should select particles from that distribution function. And that distribution function is a function which specifies the fraction of mass or fraction of particles that you need to include in your orbit in your simulation for a given E and L. If you use actions, which you can also do then for a given set of actions. And you want the particles that you select to reflect those fractions. And the amount of number of particles of a given E and L wants to be that specified by the distribution function. Now, almost everybody does this the wrong way, and I don't know very many people who do this in the right way. If you do the wrong thing, which is what most people do, you generate coordinates. You just choose particles within your volume and within the energy range that you've got by choosing at random the position and then velocities of particles. And then you ask what is the value of the distribution function for those at that point in space, in phase space, and then you decide I'm going to accept or reject this particle on the basis of the value of the distribution function at that point. And that means that having adopted this procedure, you are bound to have the difference between the distribution function that you're trying to create and the distribution function you actually create is different by shock noise. And so you don't really want that to happen. And the Galaxy code provides a way of getting over that. So if you select particles in a smooth way from the distribution function in the way that Galaxy code provides, then you force the fractions of orbits in any individual value of E and L to be given by the distribution function. There are still additional things that you need to choose in order to select the actual position of particles, but those are just the phases of the particle in its orbit for a given particular set of integrals. And so you can choose those phases around the orbit at random, but at least you have nailed right at the beginning that you're getting selecting particles from the distribution function in the way that is specified by that distribution function. And if you look at this figure here, you can see that it really helps. If you try to set up an equilibrium model that's unstable, in this case it was an isochrone disk, and the model was expected to be have an instability to form a bar, and you're measuring the pattern speed and growth rate of the instability from the simulation. The distribution of red points shows what you get if you do that by selecting particles from the distribution function in the manner that Galaxy Code recommends. If you use the alternative method of selecting particles from random, then the spread of values that you get from just, this is each one of those, I think, is 10 different simulations starting with different random seeds selected from the same distribution function, but by random methods. You can see that the spread is several times larger than the spread with the smooth distribution function. So you're going to get a much closer, more faithful behavior of the model if you select particles in this way. And it doesn't seem to matter very much how you select the particles in phase. So please, if you're going to set up equilibrium models, please try to use this method, because if you use the random approach, which most people do, you will seed your model. Your model will be a much worse initial model to start from. Now, since you don't have, there are very few mathematical expressions that you can find in the literature which tells you what the distribution function is for some particular model. There are some, but there are not a lot. That presents a problem, because you really don't want to be just working with an analytic Kuszmin-Tumry disk or something like that. You want to use realistic galaxy models with disks and halos, and so you really there are no distribution functions for disks embedded in halos that I know of in the literature. And there's this Vasiliev, who works in Cambridge, has a Nagama package which is extremely powerful, which will derive distribution functions as functions of actions in any arbitrary for any arbitrary model, and that will give you very nice initial distribution functions. They solve them by iterative method. Unfortunately, after he's got the distribution function properly by this method, he then spoils his elegant approach by randomly selecting particles from those distribution functions. So he does it exactly the way you're not supposed to do it, which is unfortunate. But you can do better. You can use his distribution functions that come from the Sagama package, and then select the particles using the method that I recommend. But Galaxy also provides methods to create disks, distribution functions in disks, which is Shu's method, or which works in any general disk in any general potential. And then 3 methods to set up composite disk bulge halo models. You can use an iterative approach, which is similar to what Vasiliev does, or you can try using halo compression, or you can try using Eddington inversion. All 3 of these methods exist are provided by the Galaxy Code, and it enables you to set up a distribution function for the halo and also the bulge, if you want, in the presence of other mass components like the bulge or the disk. So working hard at that has been an important part of what I've achieved over the years. All right, so having got your equilibrium model and you've decided how to scale the model to the grid, and you're almost ready to go, you have to choose a time step. And it's important to choose a time step. The Galaxy Code does not choose that automatically. You have to set that as a parameter from the data cards. And you want to choose that time step to be determined short enough that you can integrate orbits on the shortest time scale with reasonable accuracy. And I like to arrange it so that you take 200 steps for an orbit in the shortest period orbit in your simulation. That's excessive. Probably 100 would be adequate, but I always like to err on the side of caution and keep the time step nice and short. But right at the center of your model, where the density is high, the orbit timescale is short, and so that determines the basic time step of your simulation. But farther out in the model, the density, the timescales are longer, and it's inefficient to use the same time step for particles farther out in the model than near the center. So you can divide the model, and the Galaxy code provides code to do this. You divide the model into the volume into zones where longer time steps can be used. And when a particle crosses the boundary between one zone and the other, it changes time step. And I would recommend that you have only a factor 2 change at each zone boundary, but by having 5 zones, for example, particles in the outer part of the grid move on time steps 32 times longer than those in the inner part, and that really makes a difference. You don't have to, it speeds up the calculation very significantly if you do that. There is another option, and that is to use guard radii, which unfortunately many people have misunderstood. You can subdivide time steps below the basic time step that you've chosen for the shortest period orbit in your simulation, if you wish, using these guard zones, where you can integrate the orbit on shorter time steps still, without calculating the gravitational field at every step. That is fine if the force is dominated by the fixed field. So if you've got a dense bulge which is rigid, or a point mass, or a dense mass concentration at the center, where the force that comes from that rigid material is much greater than the self-consistent field that's coming from the particles, then it's okay to subdivide the time steps and integrate the orbit around the dense center by shorter time steps. In fact, that's a good idea. But you can only do that provided that the attraction from the particles is a negligible or small part of the total field. If the attraction from the particles is large, then you're doing the calculation incorrectly, and you should really be using a shorter overall time step in the simulation. So this is good when you've got a fixed mass in the center where the field becomes extremely strong and dominates over the distant field from the particles. But that's the only time in which it's safe to use these guard radii. And one or two people I noticed have been making the mistake of trying to use guard radii to subdivide the time steps back. How am I doing for time? Okay. One of the features of the Galaxy code is that the analysis of the particles is done as the simulation evolves. So I calculate Fourier decomposition of the mass distribution. I calculate the velocity moments of the particles in boxes. I calculate the density profile of the model in many different possible ways of analyzing the model, and they're all done in the Galaxy code as the model evolves, and the results of each piece of analysis, which you can turn on or turn off by your own at will, are saved in a separate file. And that means that you do not need to have frequent dumps of the particle coordinates, which if you've got millions of particles, you need 6 phase-space coordinates for each particle, and you need that at frequent intervals in order to do a decent analysis of the results. You end up with huge amounts of data on disks. I know disk space is cheap, but this is I don't see that as a reason for not doing it this way. And so all you have, once the results have been calculated as the simulation evolves, all you've got to do is just present the analysis in some graphical way for your paper by using the information which has been saved from the simulation. Of course, that means you can only use the information that was saved, if you forget to say something, then of course that is not going to be possible to use that information. So you might need to rerun it to get the information that you forgot to extract, or even you might need to try to determine something new from the distribution of particles. And that can be, but that can be done, and because the Galaxy code is so fast and efficient, it's not unbearable to have to run a simulation a second time in order to extract information that you forgot to get the first time, or didn't realize that you needed to get. So this is not a particular weakness, and I think it's a great strength. That you can do this and then get the data, then create your figures for your paper with a relatively small amount of effort.
Sorry, Jerry. I just wanted to tell you that you have 5 minutes left.
5 minutes left. Yes, that's okay. I'm nearly done. Thank you. So I think this is my last slide, actually. So the outcome of the simulation must be physically reasonable. If you run a simulation and you do not understand why it did what it did, then you should be extremely concerned about that. Because if it's not physically reasonable, it's possible that the result was compromised by some artifact in the simulation, and you really need to understand that. So the moment that you get a surprise result from a simulation that doesn't seem physically reasonable, then you should begin immediately to worry whether it is correct. And you should stop, pause before rushing to publish something you don't understand. And it's important, even if you do understand it, to show that the outcome is insensitive to changes in the number of particles, which with the Galaxy code you can crank it up by a factor of 10, and if that makes a difference, you can crank it up by another factor 10, and you can still get have the simulation run in a reasonable amount of time, and you should find that the outcome of the simulation is not sensitive to the choice in the number of particles. And if you should also play around with changing the grid resolution to make sure that you can't do this ad nauseam, because it's quite expensive. But if you double the grid resolution, for example, then you shouldn't see the outcome of the simulation change. If you also change the time step by reasonable factors, you half the length of the time step and the outcome doesn't change, then you can be fairly confident that things are okay. You could also play around with small changes in softening length, although that's also often. If any of these tests result in significantly different behavior as a result, when you make these tests, then you should be very concerned. You should not. You should understand why that is, and then determine that your resolution that you've employed before is inadequate, and you should only publish results for which all of these statements, these tests are satisfactory. And I think this is my last slide. Yes, it is. No. Okay, so that's all I wanted to say, and I'm happy to take questions.